Welcome to Star Technology 5G. In the last video, we studied how to use timer 0 as event count. In today's video I will show you how to use serial communication. Let's start the video. Please subscribe to the Star Technology 5G and click on the bell icon. Introduction. Computer transfer data in two ways, parallel and serial. In parallel data transfers, often 8 or more lines are used to transfer data to a device that is only a few feet away. To transfer to a device located many meters away, the serial method is used. In serial communication, the data is sent one bit at a time. As you can see in the following diagram, serial communication use one data bus for transfer data. Other hand parallel communication use 8 or more buses for transfer data. Serial data communication uses two methods. Synchronous method transfers a block of data at a time. Asynchronous method transfers a single byte at a time. There are special IC chips made by many manufacturers for serial communication. UART, Universal Asynchronous Receiver Transmitter. USART, Universal Synchronous Asynchronous Receiver Transmitter. Asynchronous serial data communication is widely used for character-oriented transmission. Each character is placed in between start and stop bits. This is called framing. Block-oriented data transfers use the synchronous method. The start bit is always 1 bit, but the stop bit can be 1 or 2 bits. The start bit is always a 0, low, and stop bit is always 1, high. You can see in this figure. Here is transmitter and here is receiver. The start bit is always 0. It will goes out first. After that it will send the data bits. Bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6 and bit 7. At the end it will send 1 or 2 stop bits. PIC16F877 Serial Communication. PIC16F877 comes with inbuilt USART which can be used for synchronous-asynchronous communication. USART is a two-wire communication system in which the data flows serially. USART is also a full duplex communication, means you can send and receive data at the same time which can be used to communicate with peripheral devices. Registers used for serial communication. TXSTA, Transmit Status and Control Register. RCSTA, Receive Status and Control Register. SPBRG, USART Baud Rate Generator. TXSTA Register. The TXSTA register contains various control bits for serial communication, like master/slave mode, transmission data size bits, 8 or 9 bit, transmission enable bit, high or low baud rate selection. It is TXSTA register. Bit 7 CSRC clock source select bit. Don't care. Not use in asynchronous mode. Synchronous mode. 1 equals master mode, clock generated internally from BRG. 0 equals slave mode, clock from external source. Bit 6 TX9. 9-bit transmit enable bit. 1 equals selects 9-bit transmission. 0 equals selects 8-bit transmission. Bit 5 TXEN, transmit enable bit. 1 equals transmit enabled. 0 equals transmit disabled. Note, SREN/CREN overrides TXEN in sync mode. Bit 4 sync, USART mode select bit. 1 equals synchronous mode. 0 equals asynchronous mode. Bit 3 unimplemented, read as 0. Bit 2 BRGH, high baud rate select bit. Asynchronous mode. 1 equals high speed. 0 equals low speed. Synchronous mode. Unused in this mode. Bit 1 TRMT, transmit shift register status bit. 1 equals TSR empty. 0 equals TSR full. Bit 0 TX9D, 9th bit of transmit data, can be parity bit. RCSTA register. The RCSTA register contains various control bits for serial communication, like enable-disable serial communication, data size bits, 8 or 9-bit, synchronous-asynchronous select and framing error. Here is RCSTA register. Bit 7 SPEN, serial port enable bit. 1 equals serial port enabled. 0 equals serial port disabled. Bit 6 RX9, 9-bit receive enable bit. 1 equals selects 9-bit reception. 0 equals selects 8-bit reception. Bit 5 SREN, single receive enable bit. Asynchronous mode, don't care. Synchronous mode, master. 1 equals enable single receive. 0 equals disable single receive. This bit is cleared after reception is complete. Synchronous mode, slave. Don't care. Bit 4 CREN, continuous receive enable bit. Asynchronous mode. 1 equals enables continuous receive. 0 equals disables continuous receive. Synchronous mode. 1 equals enables continuous receive until enable bit CREN is cleared, CREN overrides SREN. 0 equals disables continuous receive. Bit 3 ADDEN, address detect enable bit. Asynchronous mode 9-bit, RX9 equals 1. 1 equals enables address detection, enables interrupt and load of the receive buffer when RSRA is set. 0 equals disables address detection, all bytes are received and 9th bit can be used as parity bit. Bit 2 FERR, framing error bit. 1 equals framing error, can be updated by reading RCREG register and receive next valid byte. 0 equals no framing error. Bit 1 OERR, overrun error bit. 1 equals overrun error, can be cleared by clearing bit CREN. 0 equals no overrun error. Bit 0 RX9D, 9th bit of received data, can be parity bit but must be calculated by user firmware. SPBRG register and baud rate. The term baud rate is used to denote the number of bits transferred per second BPS. Note that it refers to bits, not bytes. It is usually required by the protocol that each byte is transferred along with several control bits. The baud rate in the PIC16F877 is programmable. This is done with the help of SPBRG register. For a given crystal frequency, the value loaded into the SPBRG decides the baud rate. Desired baud rate equals F oscillator. Divide by 64x plus 1. To get the value of x for different baud rates we can solve the equation. PIC16F877 divides the crystal frequency, F oscillator, by 4 to get the instruction cycle. We are using 11.0592 MHz crystal, in this case instruction cycle is 2.764 MHz. The PIC16F877 UART circuitry divides the instruction cycle frequency by 16 one more before it is used by an internal timer to set the baud rate. Therefore, 2.764 MHz divided by 16 gives 172,800 Hz. This is the number used to find the SPBRG value. X equals 172,800 divide by desire baud rate minus 1. I want 9,600 baud rate. X equals 172,800 divide by 9,600. 18 minus 1. X equals 17. We will use 17 to set the 9,600 baud rate. Project: How to enable serial communication. In this project, PIC16F877 microcontroller operated from an 11.0592 MHz crystal. The RS232TX output of the microcontroller RC6 and RX input of the microcontroller RC7 pin are connected to a MAX232 level converter chip and then to the serial input of the PC using a DB9 pin type connector. We will send some characters that will show on the PC hyper terminal. Here is the circuit diagram we are using in our project. It is PIC16F877 microcontroller. Pin number 1 is master reset. If we press the switch it will reset the microcontroller. Pin RC6 and pin RC7 interfaced with MAX232. Here are the capacitors interfaced with MAX232. The value of capacitor is 10 UF. An output of MAX232 is interfaced with DB9 pins connector and other side of the DB9 pin interfaced with PC serial communication. Pin numbers 13 and 14 interface with an 11.0592 MHz crystal and 22 PF capacitors connected with the crystal. Pin number 11 and 32 connected with positive 5 volts. Pin number 12 and 31 connected with ground volt. Let's draw this circuit in Proteus. In Proteus we do not need MAX232 IC. But in practical circuit you need MAX232. I will disconnect the MAX232 IC and I will connect the virtual terminal direct with PIC16F877. The circuit is ready now. We will write its code in Micro CPIC. Here is the window where we can write the code. I already wrote the code, otherwise video gets very long. I will copy the code. And I will paste it here. Now I will define you the code. Void SERTX unsigned char x. Define data send function. TXREG equals x. Copy data into transmit buffer. While PIR1 TXIF equals 0. Wait until data transfer. Void main. Main function. RCSTA equals 0x80. Enable serial communication. TXSTA equals 0x20. Enable transmission, low baud rate and 8-bit transmission. SPBRG equals 17. 9600 baud rate, crystal 11.0592 MHz. SERTX. Bracket single quote H single quote bracket. Call SERTX and give character H. Any data we need to send, it should be written between the single quote marks. Void SERTX unsigned char X. Any data we need to send it will copy in X variable. TXREG equals X. Copy data into transmit buffer. While PIR1 TXIF equals 0. And wait until data transferred. Next it will again call SERTX. Bracket single quote E single quote bracket. Call SERTX and give character E. It will again send E character. And again call SERTXL. And send character L. SERTXL. SERTXO, and send all characters one by one. While 1. After send all character it will stay here. Now we will create the hex file. Just click on the build icon. Finished successfully. File is created. Now we will load hex file into the microcontroller. Double click on the microcontroller. Select the hex file. OK. And click on the run simulation. Now you can see all characters are transferred on virtual terminal. If you have any problem with the code, let me know in comments. Thanks for watching. Please subscribe to the Star Technology 5G. And keep watching Star Technology 5G.